Hi, welcome back. In this lecture, I would like to talk about performance modeling of MPI communication together with PingPong, that is a famous benchmark to calculate bandwidth and latency of a communication system. For modeling communication in an MPI, I will use a simple model that is called the classical postal method. So in this model, the type communication is modeled as S, that is a constant, plus a factor multiplying n, where n is the message size in byte, right? So given any MPI communication, we can measure we can actually model the time that takes to do the communication, but basically having access to three information. First, a fixed cost time that is called S, and then how large is the size, and basically another constant coming from the system that is basically the time that is taken to move 1 byte, right? S includes both hardware, so for instance gate delays, and software like a context switch or setup of the communication. So these constants that is fixed for any communication system in the postal model goes under the name of latency. R includes both hardware, as for instance raw bandwidth on interconnection and the memory system, and software. So it might be that communication system divide the message in small packages, right? So there's a cost in dividing small packages, but also for using MPI buffers, so the copies between user and system. The factor 1 over R, it goes under the name of bandwidth. So in our test to calculate the bandwidth and the latency, basically what we need to do is to measure the communication time for sending one messages, right? What we do many different tests, and we change the size of these messages, and the time for each side of the message is basically a point on these plots, where on the x-axis we have the size of the message, and then the y-axis we have the time to send a message. So this we will see from our experiments. If we do this experiment, all our points basically will lay across one line. The line is characterized by a slope. If we take the inverse of that slope, we got what is called the bandwidth. So the bandwidth is the inverse of the slope of the line that refers to the communication time. We also want to estimate the latency. So for performance estimation purposes, latency is the limit for n going to 0 of the time to send n bytes. Right? So of course we don't have any way to calculate the time to send a 0 byte message. So what we're going to do is basically still using this line, and then use this line to extrapolate at for a size matches of equal to 0. So for instance, we will extrapolate it here, and when we calculate the intercept here will be the parameter we call latency. So the standard benchmark to calculate the latency and the bandwidth is the so-called PingPong benchmark. The PingPong benchmark is a way to measure the communication time between two processes. Process 0 sends a message to process 1, and this is called ping. As soon as the P1 received the message, it sent back to process 0 another message called, and this phase is called pong, right? The time for sending a message is half of the time for the ping-pong, right? So in the ping-pong we have two messages, right? So we have the time for send the ping and the time for pong. So the time for sending a message is basically the time of the ping-pong divided by 2. So we provide on the website, on the canvas, very simple test code for performing the PingPong benchmark. The PingPong use the blocking two-sided MPI communication. So the way it is working, so we will launch an MPI code with only two processes. So we have rank 0 and the rank 1. So the one that is sending, and we also make several tests, right? And we calculate for each of these iteration what is the ping-pong time. So in this case, for instance, we have a loop count that is the number of test, and for each iteration we divide what rank 0 and rank 1 do. So the rank 0 is start sending a message, right? So it's sending this array A of size n of type double, so 8 byte, and then we send we send with the rank of the receiving and the tag, and we provide the communicator, right? So what the rank 1 does? Well, it needs first a matching receive, so it posts a receive, and after the receive is completed, it send back to rank 0 the message with A. So this is very simple way to do a ping from 0 to 1, and then a pong from 1 to 0. When we take the communication time, we divide it by 2, and we can make the plot that we saw in the previous slide. So we provided the code. I want to run it on our supercomputer. So to compile, I use the CC PingPong, that's the name of the code, and then this is the name of executable. So CC automatically detects that the code is using MPI, so it's going to wrap it around the MPI library. So at this point, once we compile it, we need to run. So what we are interested in most of the time is what is actually the bandwidth from one node to the other one, right? So basically we use our interconnection only when we go out of the node. If we stay on the node, the communication is only within the node, and we don't use the interconnection, right? So it's still interesting, but less interesting to actually calculate what is the real interconnection bandwidth. So if we want to do on our supercomputer, this is how to know bandwidth. So the first thing we need to do is to ask for an allocation consisting of 2 nodes, and the 2 nodes will be connected via the network. We say how long we want to have the allocation, and then we say, well, we just take Haswell nodes. Once the allocation is granted, we run srun -n, and then we use only 2 processes, so 0 and 1. So very important also is to set another flag to ensure that the 2 processes, MPI processes, are on different nodes. So for doing that, we just use the flag -, and task per node equal to 1, and then the name of the executable. Right? If you want to calculate the in node, so in the node, so we don't use interconnection, we ask only for one node with salloc, and then we basically just ask 2 processes within the node, and this will calculate the on-node bandwidth. So if I run the code on the supercomputer, what I will get is basically 2 column. The output is 2 column, one with the size in byte, right? So is 8, so that's basically one element of a type double, right? And then the time in seconds that takes for doing this communication. So we get this table out of running the PingPong, and then if we plot on x-axis the message size and the y-axis the communication time, you will see that the different point basically lay down over one line, right? So what what we are interested in is actually going from these several data points to a line, right? So we will need that line to calculate the bandwidth and the latency. So we would like to determine S and R, so that the formula communication time is equal to S plus R multiplied by N fits to this data, right? By fit we mean that the difference between S plus Rn and the communication time that we found by this point is as small as possible in some particular sense, where in some particular sense means, you know, with some norm. So one common measure is to consider the vector of values n and the corresponding values t, where t are the communication time. These are the columns that we saw in the previous table, right? And when we consider the norm of t minus s plus rn, and then we seek to minimize this norm by a technique called least square or best fit. So if we want to do a best fit, we can rely on MATLAB or in Python in particular to call a function called polyfit. So what the polyfit function does is to take the arguments, so the x and the y. So in this case, we have the size of the message in byte as our x, and then we have time for hour. Also, we need to tell polyfit what is the polynomial order that we want to fit to, right? In this case is a line, so the polynomial order is going to be 1, right? So if you call this function, we basically got it to coefficient. We got in this case p1 and p2, and this, so it's basically p1 multiplied by the size, that is independent variable, plus p2, right? So if you put the size, this array with the size and time and the execution time for the communication, we do the polyfit. So we will get two numbers. The first one is going to be p1, right? That is so it's not 1 over r, but this is 1 over the bandwidth. So this is r, and this is s. So our latency, according to this best fit, is p2, that is this number, and when we want to express in milliseconds, so we divide by 10 to the minus 6, so we get that latency is 16 milliseconds. For the bandwidth, we need to take r and take the inverse of this. So this is 1 over the bandwidth, not 1 over r. So 1 over p1, and then we want to express as a gigabyte per second. So we divide it by 1 to the 9. And what we get is 6.9 gigabytes per second, right? Of course, there are other ways to implement a PingPong, not just to rely on MPI blocking communication, so simple send and receive like in the code that we provide you. We could use, for instance, two-sided communication that is non-blocking, or other way of two-sided communication. So how would you modify the benchmark to use non-blocking communication? We could also use the one-sided MPI communication. So for instance, you can check the PingPong with the passive synchronization by Jeff Hammond provided on this GitHub. So this is the last slide of this lecture, and talk to you soon.